Welcome to Java in 3 hours. In this video, I've compiled a series of lessons where you can learn the most important concepts in Java in just 3 hours. How to use this tutorial? First of all, it's worthwhile to program along with me. Try making changes and see how it works. I use the JGrasp IDE, but you can use whatever one you want. I'll have a link to the Java JDK, which you need to install, and the Java JGrasp IDE at the end of the description for this video. Check the table of contents in the description for topics you're interested in so you can jump to them. If you're watching the video and you already know about a topic, set the video speed to playback at 1.5 or 2 times speed so you can get through it more quickly. You can hit the gear logo to change the playback speed. Leave comments with your questions or ideas. And please hit subscribe so you can get the latest content from this channel. We're going to start by learning how to write our first program. To begin with, we must declare a class. Every program in Java must have at least one class. To do so, we'll type on the first line, public, class, and then the name of our class. In Java, classes names are written in Pascal case. That means all words are run together and the first letter of every word is capitalized. I'm going to call my class my first program. Our class name must match our file name exactly, except our file name will have .java at the end. Otherwise, the program's not going to build. Next, we have to define for the computer where the class begins and ends. We do that with curly brackets. We'll start with an opening curly bracket and close with a closing curly bracket. Inside our class, we need methods. Every program must have at least one main method. That tells the computer where to start when we run the class. A main method must be written exactly like this: public, static, void, main, open parentheses, string with a capital S, open close hard brackets, args, close parentheses. Next, we need to define where our main method begins and ends. So we do that with curly brackets again. Our main method begins after this curly bracket and ends after that curly bracket. An important rule with curly brackets is when we open one, everything after that is indented one more line. When we close one, everything after that is indented one less line. The next command we're going to learn is the system out print line. What that'll do is let us output something to our console down here. So we have system with a capital S, period, OUT, dot period, print, ln. And then we have an open close parentheses. Inside here is the information or the data we want to go to the console. In this case, we're going to use something called a string literal. A string literal is some very specific text or numbers. So we're going to open and close parentheses. That lets the computer know there's going to be a string literal inside here. And my message is going to be hello world. We must end this line with a semicolon. Certain lines of code must end with a semicolon, like system out print lines. Other ones, like public static void main or the class name, do not end with a semicolon. We have an open and close bracket to define where the main method or the class begins and ends. Let's check if we did everything right. What we're going to do is we're going to go to build and compile. This might look different if you're using a different IDE, but it'll be the exact same concept. What this does is checks the program for errors and converts it to bytecode, which the computer can run. This didn't give us any errors. That means, as far as it can tell, we didn't make any mistakes. Now, this is ready to be run. So I'm going to go to build, run, and our program ran and outputted hello world to our console. I'm using the JGrasp IDE in this video. Tell me in the comments, what is your IDE of choice? In this lesson, we are going to learn about using variables. Variables are letters or words that can store and manipulate data for us. I'm going to start by declaring a variable inside the main method. Variables declared inside a method are called local variables because they are local to the method that we've created them inside. So I'm going to declare a variable x of type int x. Ints can hold any whole number within a large range. Next, we need to initialize x. We need to give it an initial value before we really do anything with it. I'm going to initialize x by setting it equal to 10. Now that it has an initial value, I can change the value to 5. I can increment it. For example, I could set x equal to x plus 1. This is going to take the current value of x, which is 5, add 1 to it, it'll become 6, and that number 6 will become the new value of x. In Java, we can think of the single equals sign as being like a left-pointing arrow. The data on the right side of this expression will be calculated and then go into the left side of the expression, which is holding the variable x. The naming conventions for variables in Java is lower camel case. It's the same with method names. That means if we have one word or letter, it starts off and is lowercase. If we have multiple words, they're all run together with no spaces, and the first letter of every word except for the first word is capitalized. So I'm going to declare another int. I'm going to call it my final score. I have 3 words. They all run together. The second and third word start with a capital letter. The first word starts with a lowercase letter. In this case, I'm going to choose to declare and initialize on the same line. Now what I want to do is I want to output the value of one of my variables. So I'm going to say system out println, open close parentheses. I want to output the value that is stored inside the variable. I'm going to choose my final score. Notice there aren't quotation marks around my final score. If there were, it would print out my final score. Since there's no quotation marks, it's going to output the value stored inside the variable, my final score. Let's end our system out println with a semicolon. Next, let's build it. We're going to go to Build, Compile. The compiler checked to see if it could find any errors and convert it to bytecode. So far, it looks like there isn't a problem, so we're going to run it. We're going to go to Build, Run, and it outputted the value stored in my final score, which was 10, to our console. If you're enjoying this video, please hit the like button and leave me a comment with your feedback. In this Java tutorial, we are going to learn about the 8 primitive data types that are built into Java. The first 4 are byte, short, int, and long. These all hold integer values, but within different ranges. The next 2, float and double, hold decimals, but double has more precision. Next, Boolean can hold either true or false. And finally, char or char can hold a single character. The ones we're going to focus on are int, double, and Boolean, because these are among the most useful. Let's start by declaring an int, a, and setting it equal to the whole number 3. Next, let's create a double, b, and set it equal to 3.0. The compiler knows that this is an int because it doesn't have a decimal, and it knows this is a double because it does have a decimal, even though these two values are equal. If we want, we could set b equal to the integer 3, and the compiler would know to convert this to 3.0 for a double. However, it doesn't work the other way around. If we typed in a equals 3.0, it would not know to convert it because it would fear a loss of precision. So the error we're going to get here is incompatible types, possible lossy conversion. We can make this work by using something called casting. Casting converts it to another data type. We're going to cast this 3.0 as an int, so it will cut off everything after the decimal point before assigning the value to a. We need to be careful with this because if the value were 3.999, it would cut off everything after the decimal point, and then a would equal 3. It's important to know that casting a double to an int does not involve rounding. It involves cutting everything off after the decimal. And there is our value 3. Next, let's look at a Boolean. We'll create a Boolean C. We'll set it equal to true. We could change it later, set it equal to false if we wanted. In this Java tutorial, we are going to review the simple assignment operator. We are going to learn about the arithmetic operators, and we are going to learn about the unary operators. So first, let's review the simple assignment operator. We could use it in an example. We have int x, we declared x. We want to set x equal to 3, so we would do that. The simple assignment operator, which uses a single equal sign, it can be thought of as a left-pointing arrow. Whatever is on the right side of the expression is calculated and put into the variable on the left side of the expression. Now let's talk about the arithmetic operators. We could use them two ways. First, we could say system out print line and have it calculate whatever was inside here. So it would do 3 plus 3, which would be 6, and then it would output the number 6. We could also use subtraction, multiplication, or division. Division is handled differently depending on whether we are dealing with an int primitive type or a double primitive type. We can also use it to change the value of a variable. For example, we could say x equals 3 times 3. Or if we wanted to modify the value of x based on an old value of x, we could say x equals 3 times x, which would take the old value of x, multiply it by 3, and then take that product and put it as the new value of x. The one arithmetic operator you might not be familiar with is the mod operator, or the remainder operator. How this works is we would divide the first number by the second number, and then we would take the remainder. So for example, 3 goes into 4 one complete time, and then there is a remainder of 1. So in this case, it would output the number 1, because that is the remainder. There we go, our number 1. If we did 11 mod 3, 3 goes into 11 3 full times, and would leave a remainder of 2, so this would output 2. Finally, let's look at the unary operators. They can be used for shortcuts. For example, if we had x equals x plus 1, that would take the old value of x, add 1, and make that the new value of x. We could simplify that by saying x plus plus, which is just shorthand for x equals x plus 1. Same thing with x minus minus would be shorthand for x equals x minus 1. There is another shortcut that we can use with the other arithmetic operators. For example, x times equals 3 would be shorthand for x equals x times 3. Finally, we have the not operator. So if we had a Boolean z equals true, and then we wanted to say system out print line not, which is the exclamation point, z, the opposite of z, which is true, would be false. So this would print out false for us. In this Java tutorial, we are going to learn about two things. The first is how to cast a primitive value, and the second is overflow. Some important facts to know. First, casting primitive data types allows us to convert a piece of data from one primitive type to another. Widening means converting to a data type with either more precision, as in more decimal places, or more space, as in larger or smaller values. Narrowing means converting to a data type with either less precision or less space. Let's start by looking at some code. So here we have our code, here we have the data on the stack memory, and here we have some notes. We'll start by declaring a variable, a, of type double, and initializing it to be 3.0. Then we'll add it on the stack here. Next, we'll notice that here we're setting double b equal to 4. The 4 is an int, and the b is a double. This is what we call widening, because 4 needs to be widened to 4.0, adding precision. This can happen automatically, so then when we place it on the stack, it automatically converts it to 4.0. Now let's look at another example. Here we have double C equals double 5. The double here is manually casting it to a double. This is a good practice because it lets other programmers know what's going on, but it's not required in the case of widening. Here, we're declaring a variable d and setting it equal to c. This will cause an error when we compile because c needs to be narrowed to fit into an int value. Narrowing must be done manually. For example, if we said int d equals and we manually cast it as an int c, this would work. Then we would narrow the value 5.0 into the int value 5. Next, let's look at this example. We have int e, and we're casting 3.95 as an int. It's important to understand when we cast a double as an int, we lose the entire decimal portion of the number. So we don't round, we truncate after the decimal point. Therefore, e will be set equal to the int 3. Next, let's look at an example where we have to deal with overflow. Here we have int x equals 10. We'll place that on the stack. It's important to know that ints go to a value from about -2 billion up into a value of about +2 billion. Here we're declaring a variable of the primitive type byte y. We haven't initialized it yet. Bytes can have a minimum value of -128 and a maximum value of 127. On this line of code, we are setting the byte y variable equal to x. This is going to generate an error because we need to narrow x. In this case, the value of x10 is well within the range of what a byte can hold. However, the compiler is going to be concerned that x may not always be within the range we want. Therefore, we need to manually cast the int x as a byte, and then we can set y equal to it. In this case, y equals 10. There's no need for any loss of data. In this example, we're casting the number 128 as a byte. We can see positive 128 is greater than the maximum value a byte can hold. This will cause an overflow, where this number is larger than our data type can hold. In the case of byte, that means it'll roll over to the minimum value. The minimum value will be -128. Other data types can roll over too when they overflow. Byte, short, int, and long will all overflow and wrap around to the other side. The primitive type double and float will not wrap around when they overflow. Instead, they will go to infinity if the value is too high, or -infinity if the value is too low. Casting is one example of when we can have an overflow. However, we can also overflow a variable when we add past its highest value or subtract past its lowest value. In this Java tutorial, we're going to learn about how to swap the values of two variables. The most universal way to do this is with a temp variable. There are other ways to swap values without temp variables, but they only work with certain data types. We won't cover those today. Let's start by declaring a couple of variables and initializing them. We'll declare a variable x, set it equal to 3. Then we'll declare a variable y and set it equal to 9. We'll start by discussing a wrong way that many new programmers try. They set x equal to y and y equal to x, expecting that it'll swap the values of these two variables. Let's trace it to see what's going to happen. We set x equal to y, so it copies the y value to the x. Then we set y equal to x, which copies the x value to the y, and they both end up at 9. However, we wanted to swap these values. We wanted x to be 9 and y to be 3. Now let's look at the right way. We start by creating a temp variable and copying the value of x into the temp variable. Next, we copy the value of y into the variable x. Finally, we copy the value of temp into the variable y. Now the values are switched. Y is 3, x is 9, compared to the other way around. In this Java tutorial, we are going to learn about division with the int primitive type and division with the double primitive type. They behave differently. Let's start with int and let's look at some examples. For example, if we divide the number 5 divided by 3, both of these are ints, so they're going to be treated with int division. 5 divided by 3 equals 1.6 repeating. However, ints can't support any decimal portion of the number, so we'll cut everything off after the decimal and just give us an output of 1. Doubles behave differently. If one or both of the numbers is a double, it will use double division. So we divide 5.0, which is a double, by 3. It's not going to round until we get to the last digit. Dividing by 0 behaves very differently with ints versus doubles. For example, if we divide by 0, 5, which is an int, divided by 0, which is an int, we're going to get an error because we can't divide by 0 using int division. Here's our error, arithmetic exception, divide by 0. On the other hand, if we're using double division, we can divide by 0. The output will depend on the numbers. Here I'm just going to change one of the numbers to a double, and since one of the two is a double, it will treat it with double division. Since the numerator is a positive number, we are going to get a positive infinity. If the numerator were a negative number, I'm going to make this double just to show as an example, we're going to get negative infinity. If both the numerator and the denominator are 0, we are going to get NaN, which stands for not a number. So we have to be careful if we're risking dividing by 0 if we're dealing with ints. If we're dealing with doubles, we may be okay dividing by 0 because we will end up with either a positive infinity, a negative infinity, or a not a number value. In this Java tutorial, we are going to learn about Boolean expressions and how to use them with equality, relational, and conditional operators. First, let's discuss what a Boolean expression is. A Boolean expression is a mathematical expression that can evaluate either true or false. This one evaluates to true. This one evaluates to false. One of the many things we can use Boolean expressions for is inside an if statement. For example, if we say if 3 is greater than 2, then if this Boolean expression is true, the code inside these curly brackets will execute. If it is not true, it will skip the code inside the curly brackets. First, let's talk about relational operators. Relational operators are either equals or not equals. So if we say 3 equals 2, it's checking to see if these two are equal. When checking equality with primitive types, we use double equals. This is different than single equals, where one is set to the value of the other. We only want to use double equals with primitive types. There's another way to check equality with objects that we will discuss later. The other equality operator is not equal. This expression is true because 3 is not equal to 2, so the code inside the curly brackets will execute. The 4 relational operators we want to know about are greater than, less than, greater than or equal to, or less than or equal to. If we do 3 is less than or equal to 2, this is a false statement, so it will not execute the code here. We often use Boolean expressions in conjunctions with variables. For example, we might say something like x is less than or equal to 2. Next, let's talk about conditional operators. Conditional operators allow us to combine 2 or more Boolean expressions into a compound Boolean expression. For example, if we said x is less than or equal to 4 and x is less than 3, then both of these would have to be true to execute the code inside the curly brackets. Since 5 is not less than or equal to 4, it is not even going to check the second part. This is called short-circuiting. This can be important in situations where the second part of a compound Boolean expression might cause an error. For example, if we had 5 divided by 0 is greater than 3. This will cause a crash because we can't divide an int by a 0. However, since this first part is false, it's not even going to check the second part, and the program will execute without error. On the other hand, if the first part is true, it will execute the second part to check if the second part is true, to see if the full expression is true, and this will crash with an error. Arithmetic exception error, divide by 0. We also have an OR operator. OR will check if either OR is true. So for example, we could say x is greater than 3, or x is equal to 10. In this case, it won't check the second one because the first one is true. Since only one of the two needs to be true, it won't check the second one. Again, this can help us in a situation where the second one will cause a crash. Since the first one is true, it doesn't bother checking the second one and just executes the code inside the brackets. On the other hand, if the first one was not true, it has to check the second one to see if either of them are true. And of course, this will cause a crash. So remember, for AND or, we can have a short circuit situation where the second part of the expression is not evaluated because it isn't necessary. In this Java tutorial, we're going to learn about if, else if, and else. These commands allow the program to execute or not execute a block of code depending how a Boolean expression evaluates. Some important facts to know. If and else if require a Boolean expression while else does not. An else if must have an if or another else if to latch onto. We'll discuss how this works in a later slide. Also, an else must have an if or an else if to latch onto. Let's write a code with several if expressions. If expressions are unconnected to each other unless they are nested within each other. So 1, 2, 3, or none of these statements could execute independently. Let's trace the code here. We start off by declaring x and setting it equal to 5. Next, we evaluate the Boolean expression in the first if statement. X is less than 10, whereas x equals 5, this is a true statement. So we execute the block of code attached to the if and output the letter A. Next, we evaluate the Boolean expression in the next if statement. X is less than 4, this is a false statement, so we skip the block of code. Finally, we evaluate the expression x is less than 7. This statement is true, so we execute the attached block of code and output the letter C. Now let's move on and look at else statements. Here we've got a block of code that has an if or an else. This else latches on to this if in such a way that if this Boolean expression is true, the if's block of code will execute, or if this Boolean expression is false, the else's block of code will execute. Let's trace this out. We start off by declaring y is equal to 5. We evaluate the Boolean expression y is greater than 10. This expression is false, so we execute the block of code attached to else, and we output the letter E. Next, we're going to take a look at else if statements. So we've got an if, two else ifs, and an else. This section of code must be considered together. Here's how it's going to work. We have an if statement. If this if statement evaluates to true, we'll execute its block of code and ignore all the else ifs and else. If it evaluates as false, we will continue on to the else if. If this first else if evaluates to true, we will execute this block of code and skip everything else. We will keep doing that until we hit the final else. If nothing evaluates to true, then we will execute the block of code attached to the else. Let's trace this out. We start off by declaring z and initializing it to 5. Next, we evaluate the expression z is greater than 10. This expression is false, so we skip the ifs block of code and continue on to the else if. The else if expression z is greater than or equal to 4. This is true, so we execute the block of code attached to the else if, output g, and skip everything else. Next, we are going to look at another way to attach code to an if or an else expression. If we are only using one line of code, we don't need to include the curly brackets. We just indent it to let other programmers know that it is part of the if, the else if, or the else. Remember, this only works if we only have one line of code. Next, let's look at some common mistakes programmers make. The first is to put a semicolon after the if, the else if, or the else. This takes that statement out of the equation and will execute the block of code in the curly brackets regardless. Another problem this can cause is if we have an else, we will get a compiler error that says else without an if. That's because the else doesn't see the if and can't latch on to it because there is a separate block of code in between it that is not attached to the if. Another mistake programmers sometimes make is they attach a Boolean expression to an else statement. Only if and else ifs need a Boolean expression. Elses do not. Another mistake that programmers sometimes make is they forget to add curly brackets if they want to have more than one line of code attached to an if or an else if. In this case, since we have two lines of code, we need to use the curly brackets to denote the beginning and the end of the code attached to this if. In this Java tutorial, we are going to learn about nested if, else if, and else statements. Some important facts. An if, else if, and else can be nested inside a block of code attached to another if, else if, and else. Other control structures like while, do while, for, and others can also be nested inside each other. Let's look at a sample of some code. Here we have an outer if-else statement, and inside the if we have a secondary if, else if, and else statement, and inside the else block of code we have another if and else if statement. These statements will only be evaluated if this Boolean expression is true. These statements will only be evaluated if this Boolean expression is false. Let's examine this code more closely. It can be helpful when preparing to trace a series of if and else statements to first identify which ones are attached to the other ones. First, we can see that this if is attached to this else. So depending on how this Boolean expression evaluates, we'll either do this block of code or this block of code. If we end up running this block of code, we can make a notation that these if, else if, and else are connected. This else if will check if this Boolean expression is false, and if both of these Boolean expressions are false, this block of code will run. On the other hand, in our else block, this if and this else if are attached. If this Boolean expression evaluates to true, we will run this line of code. If this doesn't evaluate to true, we will check this line of code, and if this one does evaluate to true, we will run this line of code. If neither of these Boolean expressions evaluate to true, we won't do either of them. Now let's try tracing this code. First, we're going to start by declaring x is equal to 5, and that'll appear on our stack. Next, we're going to declare y and set it equal to 3, which also appears on our stack. Now we evaluate this Boolean expression, x is less than 10. X is in fact less than 10. This evaluates to true, so we will run this block of code. Next, we evaluate the y is not equal to 3. Y is in fact equal to 3, so this is a false statement. And we're going to go on and check this second Boolean expression attached to this else if. Y is less than or equal to 5, so this evaluates to true, and we output B. Since we found one that is true, we don't have to continue on, and we end up terminating our program. In this Java tutorial, we are going to learn about operator precedence. This is sometimes also called order of execution or order of operation. Some important facts to know. Like in math, some operators will be processed first, depending on their precedence. If precedence is the same, most operations are generally processed left to right like in math. It is best to use parentheses to clarify the order of execution. We want to make it as easy as possible for other programmers to understand our code, even if they don't have a perfect understanding of order of execution. Let's look at this simplified table to let us know what comes first and last. This will cover about 99% of the circumstances you're going to run into. We can see we start with parentheses, then increment and decrement and not, then casting, like casting to an int or a double. Then we have multiplication, division, mod, addition or concatenation and subtraction, all the comparative operators, and an or. For the most part, you're just going to have to worry about the ones highlighted in yellow here. Now let's look at some code that we can trace out. We see the SOP. For the purpose of this video, this stands for System Out Print Line. We have our representation of our memory stack here, and then our output. For ease of viewing, I've color-coded the parentheses to indicate their level. So the outermost will be red, then the middle ones are green, and then the innermost are blue. Let's start tracing out the code. We'll start by declaring x and setting it equal to 5, and we see it appears on the stack. Then we'll declare y and set it equal to 6, and we see it's also here on the stack. Since parentheses have the highest precedence, we're going to look for the innermost parentheses, which are right here. There's only one operator inside these parentheses, subtraction, so we're going to evaluate 5 minus 2, which gives us 3. Next, we have to look at the other parentheses. We have two green parentheses. However, this one is further left, so this one is going to take precedence. Inside these parentheses, we have two operations, subtraction and multiplication. We can see multiplication takes precedence, so we're going to go and do 1 times 2, which will be 2. We have one more operation inside these green parentheses, 3 minus 2, which gives us 1. Now, we are finished with this set of parentheses, so we'll go over to this other green set of parentheses. There's only one operation left inside here, 3 times 3, so that'll evaluate to 9. Next, we are in our outermost set of parentheses. So we've got several different operations. We've got a cast, we've got a plus plus incrementation, we've got division, and we've got a greater than. We can see the plus plus increment, it takes highest precedence. So we'll do x plus plus. Since the plus plus is after the variable, this means that we will increase the value of x in the stack, but for the purpose of this x, it will remain at 5. For more information on this, please click on the link in the upper right-hand corner of this screen. Now, we'll replace this x with a 5 as we increase the value on the stack to 6. Next is cast. So we're going to cast this 5 as a double, and 5 as a double is 5.0. Now we see next is division. So we'll do 5.0 divided by 1, which will remain 5.0. We have one final operation that's checking is 5.0 greater than 9. This evaluates to false. So now we system out print line false, and then we output it to the console here. In this Java tutorial, we are going to learn how to use the scanner class to take input from the user in the console. So the first thing we have to do, even before we create a class, is we have to import the scanner class. We're going to say import java.util.scanner with a capital S. We'll hit a semicolon there. Next, we can create the class like we normally do. So we're going to call this public class user input. Then we'll open and close the class. We're going to create a main method, public static void main string array args. Open and close this. The next thing we need to do is we need to create an instance of the scanner class. So we're going to declare a variable of type scanner. Since scanner is an object type variable, we started with a capital S. Then we'll call our variable keyboard. People generally call it keyboard or KBD. It doesn't matter, but pick a variable name that makes sense. Now we need to initialize a variable, so we'll say equals new scanner, open close parentheses, system with a capital S .in, and end with a semicolon. So we can use this variable, which is pointing at a scanner object, to take input from the console here. We're going to start by learning how to use the scanner object to take input for 3 primitive type Boolean, int, and double. So we'll start by declaring a double. We'll call it x, and we'll say equals keyboard dot next double, and then open close parentheses and end with a semicolon. Now when we run it, we're going to notice that it just kind of hangs here. And that's because it's waiting for us to enter in a double before it can continue. So I can enter in a double 12.3, and then it finishes the program. Now generally it makes sense to let the user know what you want. So I'm going to say system out print line type in your height. So now when I run it, it's going to say type in your height, and it's going to pause to wait for me to type in the next double, and then it's going to finish. So I'm going to say 55.0. And there we go. Now we're going to add some more code. We're going to do this with an int and then with a Boolean. So for an int, it's going to be almost the same. We're going to say int y equals keyboard dot next with a lowercase n, int, open close parentheses. And we also want some text to let the user know what information we want. So we'll say, what is your age? So then when we run it, it's going to first ask us your height. Then it's waiting for us to type in our height. So I'm going to say 55.9. Then it's going to say, what is your age? And it's waiting for us to enter in our age. So I'll say 32 and hit enter, and then it finishes the program. So now we're going to do it with a Boolean. And we're going to say Boolean. Now x and y are bad variable names for this because they don't really explain what the purpose of the variable is. So I'm going to say is female. And then I'm going to say equals keyboard dot next Boolean, open close parentheses. I'm going to say system out print line. I'm going to say are you female? And I'm going to let the user know we want it in true false, because if we enter the wrong data type, it's going to crash the program. So end with a semicolon. I'm going to run it. We're asking height 55, age 21, and are you female? False. All right, the last thing we're going to do is we're going to learn how to take strings in. So I'm going to say string name, and I'm going to set it equal to keyboard dot next. People expect it's going to be next string, but no, it's dot next. Now this will only take the first word, takes the first word on a line. So if you type several different words separated by a space, it's only going to take the first one. If we wanted to say string like full name and get all the words on the line, we would say keyboard.next line, open close parentheses. The thing to be careful about is if you switch back and forth between next line and next, or next line and some of these other ones like next boolean, next int, you will sometimes have problems where we'll skip over one. So I'd recommend using against next line unless you're going to be using next line exclusively. So we'll say takes the entire line of text and say be careful using in combination with other dot nexts. So that explains how you use the scanner class to take user input from the console. In this Java tutorial, we're going to learn about for loops. For loops let us repeat a command or commands. Each for loop declares a variable that acts as a counter. The counter variable will monitor the progression of the loop, but can also be used inside the loop for various purposes. We'll learn some more about some of these various purposes in later videos. Let's start by declaring a for loop. The header of the for loop has three parts. The first part declares and initializes a variable that acts as a counter. The second part, the test expression, checks to see if the for loop will continue. Finally, the update for the variable will happen at the end of each cycle of the for loop. In this case, I will be incremented by 1. Let's add some code inside the body of the loop. In this case, we're going to print out the value of the counter variable I. Let's trace out this loop. We'll start by declaring int I and setting it equal to 0. Next, we check, is I less than 4? It is, so we may continue with the loop. We print off the value of I, which is in this case 0. At the end of the loop, we increment I by 1 to become 1. Next, we check, is I still less than 4? It is, so we may continue the loop. We again print off the value of I, in this case 1. At the bottom of the loop, we again increment the value I by 1, in this case to 2. We check, is I still less than 4? It is, so we may continue with the loop. We print off the value of I, which is 2. We increment the value of I to 3. We check, is I still less than 4? It is. We print off the value of I, which is 3. We increment the value of I by 1, and now it becomes 4. We check, is the value of I less than 4? It is no longer less than 4. This Boolean expression is false, so we terminate the loop and continue on to any code after the loop. In this Java tutorial, we will learn about while loops and the similar do-while loops. While loops repeat commands while a Boolean expression remains true. Do-while loops checks the Boolean expression at the end of the loop and will always run at least once. Let's look at a very simple while loop. This one, while true, will always evaluate to true, so the body of the loop will execute forever. Now let's look at a slightly more complex while loop. This one says while I is greater than 0. We see I is initialized to 4, so it will run, execute the code in the body, go back up to the top, evaluate to true again. Because the value I is never changed inside the body of the loop, this loop will also run forever. Now let's make a change. We add a command to decrement the value of I. As such, the loop will no longer run forever. Actually, we could have written a very similar loop using the for loop. Let's take a look at that. Here we have for, start off I equal to 4. We continue running as long as I is greater than 4. and at the end of each loop, we decrement the value of I by 1. Let's try tracing out this while loop. We start by declaring I and initializing it to 4. Next, we check is I greater than 0. A while loop doesn't necessarily run even one time. If this first evaluates to false, we will skip over the entire body of the while loop. Since this evaluates to true, we will continue on and execute the body of the while loop. System out print line I, which is currently equal to 4. Then we decrement the value of I by 1. Then we go back to the top, check is I still greater than 0. It is. Continue on into the body of the loop again, output the value of I, which is 3. Decrement I by 1. Go back and check is I still greater than 0. It is. Output the value of I. Decrement the value of I. Back up to the top to check if I is still greater than 0. It is. Output the value of I. Decrement the value of I, which is now 0. Go back up to the top, see is I still greater than 0. This Boolean expression is now false, so we will terminate the loop and continue on with any code afterwards. As I mentioned before, we could have written this as a for loop. Let's look at a piece of code where it makes a little more sense to use a while loop. Here we are having the user guess the value of a secret number, in this case 23, and they'll have to keep guessing until they get the right answer. We initialize user guess equal to 0, while user guess, the variable, is not equal to the secret number 23. This loop will continue executing. Inside the body of the loop, it'll ask, guess what the number I'm thinking of. It will take user input and put the value into the user guess variable, go back up to the top, and see if user guess is still not equal to 23. The loop will keep repeating until user guess is 23. Then the loop will terminate, and the code after it will execute that says, you got it right. Another kind of loop is the do-while loop. A do-while loop checks the Boolean expression at the end of the loop. As such, a do-while loop will always execute at least one time. Let's look at this example. We have int I equals -2. It says do, so we'll execute system out print line I, decrement I by 1. Then we check is I greater than 0. It is not, so we terminate the loop and continue onwards. Note that at the end of the while in a do-while loop, we have a semicolon. In this Java tutorial, we're going to be learning about methods. Methods are blocks of code that can be called from another part of the program. If you have a piece of code you're going to use over and over again, it makes sense to put it in a method so you don't have to rewrite it in different parts of your program. Methods may have parameters, which are a type of variable that allow us to pass data to them. Methods may return information to the part of the program that called them. For a method with a void return type, a return statement is optional. However, for a method with any other return type, it must return a piece of data of the correct type. Methods end as soon as they reach a return statement, even if there is more code in the method. Let's start by writing a simple method. We always have to have methods inside a class. However, for the sake of saving space, we're not going to put the class code at the top and the bottom. We start by writing our main method. The main method always has to be written like this: public static void main string args. A main method is the only method that will run automatically when a program is run. Now let's write a second method. This method, public static int. It's int, so that means we have to return a piece of data of int type. I've named it add2nums, and I've given it 2 parameters, which are a type of variable that allows the method to accept data when it is called. We can use these parameters to customize the behavior of the method. In this case, we're going to add num1 and num2 and put them inside a variable called total. Then we're going to return total. Here is a command that calls the method. We see that this call has two arguments. These arguments get passed to the parameters in the method. The number and type of arguments have to match the number and type of parameters in the method that it is calling. When we call this method and pass the arguments 5 and 3, it's going to add 5 plus 3 together and return the total, which is 8. However, we're not doing anything with the data that's returned, so it just disappears into the ether. It might make sense to do something like this instead. Here, we're taking the data that gets returned and putting it into a new variable called sum that we can use later. Now let's look at another method. This one is to take an average of two numbers. We've named our parameters int num_a and int num_b. We're going to use the add2nums method because if you want to take an average, first you need to add two numbers together. Instead of rewriting the code, I'm just calling add2nums, passing the data that was passed to us here, and then dividing whatever the result of add2numbers by 2 so I have the average. Next, I'm going to create a variable in the main method, avg, and set it equal to a call of the method average of 2 with the two arguments 7 and 5. Now I'm going to write a third method. This method is a void type method, so a return statement is optional. We have one parameter num3, and it's going to print out the string average is, and then concatenate that string with the value in the variable num3. Here we call the method printAverage and pass it the data inside the variable avg. Avg is not being passed, but the stack data inside avg is. Next, we're going to trace out the code. All these variables are primitive type variables, so the only data will be stored on the stack. You will see variables appearing and disappearing on the stack as they are created and destroyed. You'll also see variables grayed out as they move out of scope and then turn black again as they move back into scope. Later on, we'll learn more about the ins and outs of how scope works. We'll start here. We create the variable sum on the stack, and then we call the method add2nums and pass it the arguments 5 and 3. These 5 and 3 get passed to the parameters num1 and num2, and they're created on the stack here. Next, we create the variable total and set it equal to num1 plus num2, 5 plus 3 equals 8. Finally, we return total. Total is 8, so it takes the place of this add2nums 5, 3. Finally, we set the return of 8 equal to sum. Next, we're going to create the variable on the stack, avg, and set it equal to whatever is returned by average of 2 when we pass it the arguments 7 and 5. The variables go to these parameters num_a and num_b. Next, we have to call add2nums and pass it the 5 and the 7. The 5 and the 7 go into the parameters of add2nums, and we can see it on the stack right here. Next, we create this local variable total, set it equal to num1 plus num2, 7 plus 5 equals 12. Then we return the data inside the variable total, and it goes here. Next, we have to do this division, 12 divided by 2, and that gives us the average, which is 6. Now we'll return that 6 to where it was called. Average will get set to equal 6, and it's placed right here on the stack. Finally, we're going to call the method printAverage and pass it whatever value is inside the variable avg. The number 6 gets passed to the parameter num3, and that gets created on the stack. Next, we call systemoutPrintLine. We concatenate the string literal average is with the data inside the variable num3, so we get average is 6. Some final information on methods. A method can have multiple return statements, but only one is activated every time the method is run. Depending on the flow of the program, one return statement may be used once, and another one may be used another time. You must have the same number, type, and order of arguments as you do for parameters. The arguments must match the parameters. In this Java tutorial, we're going to learn about the math class. Some important facts. First, the math class in Java contains a variety of methods that perform different mathematical functions. Second, all methods in the math class are static. We'll learn about static versus non-static methods later on. Third, you can't extend or create an instance of the math class. Let's look at this first method, the ABS method in math. You can pass it an int, a double, a float, or a long, and it will return the absolute value of whatever data type you sent. For example, if we send it the double, negative 3.2 in these parentheses, it will return the double, positive 3.2. Next, let's look at math.pow. We can pass a combination of two ints, doubles, floats, or longs. We can mix and match those primitive types. Math.pow will always return a double regardless of what data type we send it. Here is an example. In this case, we want to take 3 and put it to the power of 2. So we put our base, a comma, and then our exponent. In this case, our base is an int and our exponent is a double, but it wouldn't have to be this way. 3 to the second power will be 9, so it will return the double 9.0. Next, we have math.sqrt. You can pass either an int, a double, a float, or a long. Math.sqrt will always return a double no matter what data type you send it. Let's look at this example. Math.sqrt, and we're sending the argument an int 9, and it will return 3.0 because 3 is the square root of 9. Now let's look at this. This is not actually a method. This is a public variable, so we are actually accessing a variable inside the math class. This is a public variable, so we can access it without a getter method. Math.pi is a double variable that is approximately equal to the mathematical constant pi. For example, the variable circumference equals 2 times math.pi times radius. You will notice that there is no open-close parentheses after math.pi. That's because pi is a variable and not a method like the others. Let's look at some other useful methods. Math.cos, so this will give us the cosine of whatever angle we put in these parentheses. Math.sin will send us the sine of whatever angle we put in these parentheses. Math.tan will send us the tangent of whatever angle we put in these parentheses. Math.log will send us the natural logarithm of the number in these parentheses. Math.max will take in two values and return the maximum. Math.min will take in two values and return the minimum. Math.round will return a round number. There are a number of other methods, and you can see the details of all the methods in the math class by checking the reference document for the math class in Java. In this Java tutorial, we're going to learn about creating one- and two-dimensional arrays. Arrays can hold multiple different values of the same data type in one variable. Arrays are objects, but their indexes may hold primitive types or reference types. Arrays in Java and most languages start off at index 0. Let's look at the two ways we can create arrays. First, we can declare the variable type, add a set of square brackets, letting the compiler know that this variable will point to a one-dimensional array, and have the variable name. Next, we say that we are creating a new, whatever data type, and then the number of indexes inside square brackets. This could be done on two lines, where we declared the variable on one line and initialized it on the next. If we don't specify the values In this case, they will default to 0 because it is an int. If it were a double array, they would default to 0.0. If it were a Boolean array, they would default to false. And if it was any type of object array, the values would default to null. Another way to create an array is, again, variable data type, square brackets indicating a one-dimensional array, and variable name, and then set it equal to a hard-coded array. This array is size 4 because it has 4 elements, separated by commas, with curly brackets at the beginning and the end. Let's see how we can change the values inside an index. This command says we want to change index 2 of the array x is pointing at to 12. Index 0, 1, 2 is changed to 12. Let's look at another line of code. This is saying we want to change index 4 at whatever array y is pointing at to 21. 0, 1, 2, 3, 4. There is no index 4, so we're going to get an out of bounds exception and the program will crash. If we want to access data inside the variable, we do it like any other variable, except not only do we specify the variable name, but we specify what index we want to access. This line of code will print out whatever value is in y index 1. In this case, that will be 5. Now let's look at two-dimensional arrays. A two-dimensional array is really an array of arrays. Here, we are creating a two-dimensional array. We again have the data type, but now we have 2 sets of square brackets, letting the compiler know that this will point at a two-dimensional array. A, and we say new int, and the number of rows and the number of columns. This is the way we generally draw it out for tracing, but it's not necessarily the most accurate representation of what's really going on. Really, we have 2 sets of one-dimensional arrays. We have the outer array with 3 indexes, and then each of the inner arrays has 4 indexes. However, for tracing purposes, it's usually easier to use this visualization. Here's another way we can create a two-dimensional array. Again, we declare the variable and hard-code one-dimensional arrays into it. You can see we have our outer array, then we have our 2 one-dimensional inner arrays. This would be an array with 2 rows, and each of the rows would have 1, 2, 3 columns. Some programmers prefer to write it like this, so it's easier to match up the first row and the second row when we are visualizing it. In this Java tutorial, we are going to learn about traversing a one-dimensional array. Some important facts to know. Arrays in Java and most languages start at index 0. That means the first index will actually be index 0. Dot length will return the number of indexes in an array. Since the indexes start at index 0, that means an array of size 5 will have indexes 0, 1, 2, 3, and 4. You can traverse an array with a for loop or a for each loop. Let's start writing some code. Here we're declaring an array x and setting it equal to 2158. And here we can see the reference variable x on the stack and the array on the heap. Now let's write some code to traverse it with a for loop. Before watching this, you'll want to be familiar with how a for loop works. For more information on this, please click on the link in the upper right-hand corner of the screen. So, we see we're starting by declaring our counter variable, int I, and setting it equal to 0. We're going to continue the loop as long as I is less than x.length. So in this case, x.length is going to return 4 because this array has a size of 4. At the end of each loop, we're going to increment I by 1. I++ is short for I equals I plus 1. Inside the loop, we're going to print out x, index I, and then a space, so all the numbers don't run together. So let's trace this out. We'll start by declaring I and setting it equal to 0, and that gets placed on the stack. Now we're going to check is I less than x.length, So 0 is less than 4, so this is true. We continue along with the loop. Then we print out x index 0, which is the number 2, and a space. We get to the end of the loop, so we increment I to 1. So now I equals 1, and we're going to be looking at index 1 on the array. We check, is I less than x dot length? 1 is less than 4, so we continue. We print out x index I is 1, so we print out the number 1, which is in index 1, and then a space. Get to the end of the loop, increment I by 1, now I equals 2. We check, is I still less than the length of the array? It is, so we continue the loop. We print out x index 2, which is 5, and then a space. Now we increment I to 3. We check, is 3 less than the length of x, which is 4, so that's true. We print out x index 3, which is the number 8, and then a space. We increment I to 4. We check, is 4 less than the length of the array? So is 4 less than 4? It is false. So we terminate the loop. So now we've gone through the loop and we've printed out the contents of the array. Now let's look at some modifications we can make to the for loop. Here, we're incrementing by 2 instead of 1. So every time we get to the end of the for loop, we set I equal to I plus 2. So I'll start out at 0, go to 2, and then go to 4. Let's look at another modification. We could start out our counter I at 1. So we'd start by printing out index 1 and then continue on like that. Another modification we could make to this code is instead of printing out the data, we could modify the data. So here we're taking the data inside x index I, multiplying it by 2, and taking the product and returning it back into x index I. So if we ran this code, it would go through the array and double the data inside each index. Now let's look at a way to traverse the array using a for each loop. You can see a for each loop has two parts. The first part is a temporary variable. I named mine t. The temporary variable has to be of the data type that's inside the array. So since this is an array of ints, I've made my temporary variable an int. Then we have a colon, and then we have the name of the array, in this case x. A for each loop will go through one time for each index in an array. Each time it goes through, the temporary variable will hold the value inside each of the indexes. So the first time through, t will hold 2, the second time through it'll hold 1, and so on. So let's trace this out. We start by declaring t and setting it equal to the value inside index 0, so t equals 2. Now we're going to print off t and a space. Now we'll move t to index 1, so t will hold the number 1. Then we'll print off the value of t, which is 1. We'll go through again. T will take out the value 5. Then we print off the value of t. Our last time through, t will pull out the value 8. Then we'll print off the value t. There are some limitations to the for each loop. With the for loop, we could skip certain indexes, but a for each loop will go through all of the indexes in the array. Also, in a for each loop, we're able to modify the data inside the indexes, and we can't do that with a for each loop. While a for each loop can be easier to use, its limitations mean it might not be appropriate in certain circumstances. In the full Java curriculum, we also cover how to traverse a two-dimensional array. To learn about that, please click on the video link in the upper right-hand corner of this screen. In this Java tutorial, we are going to discuss primitive type variables and reference type variables and how they are handled in memory. 4 important things to know. First, all data for primitive type variables is stored on the stack. Second, for reference types, the stack holds a pointer to the object which is on the heap. Third, when setting a reference type variable equal to another reference type variable, a copy of only the pointer is made. And fourth, certain object types can't be manipulated on the heap. These are called immutable objects. For this demonstration, we've got three boxes. The first will represent our code, the second will represent the data structure of the stack, and the third will represent the data structure of the heap. Stacks start off at the bottom and go up to the top. However, when you are tracing your own code or code for a quiz or test, I recommend you start off at the top and go to the bottom because it makes things a little simpler. Our first line of code, we declare a variable a of type int and set it equal to 3. Since a is a primitive type, all data is stored on the stack. Next, we declare a variable b of type int and set it equal to a. Since they are primitive types, we simply copy the data from a to b, and b gets its own unique entry on the stack. Here, we modify b to equal 100. We simply change the entry on the stack for b to equal 100. Next, we're going to take a look at some reference type variables. C is a reference type variable. We declare C as an integer array. We'll learn about arrays in detail later on. Integer arrays are objects. So, on the stack, we set C equal to a pointer to an object on the heap. The value of this object is an array of size 4 with values 1, 2, 3, and 4 in indexes 0, 1, 2, and 3. Remember, the only data stored in C on the stack is the pointer. Next, we declare a variable d, also of integer array type, and set it equal to C. We're going to copy the data from the stack to d. However, this simply means we are copying a pointer. Now C and D are both pointing to the same object on the heap. This line of code has us reach into the object on the heap and change index 1 to equal 99. Since C and D are both pointing to the same object, this ends up affecting both C and D. Here we are changing D again. However, we are causing D to point at a brand new object, an integer array of size 5. We move the pointer for D to point at the new integer array. C and D no longer have a connection because they are pointing at different objects on the heap. Here we are declaring another integer array, E, and having it point at a new object on the heap. Next, we create an integer array, F, and have it point to an identical object on the heap. Notice, even though the values are the same, they are separate objects on the heap. When we change the value in index 1 of the object F is pointing at to 98, it only affects F because E and F are pointing at different objects on the heap. Next, we're going to look at an immutable object. We've declared a variable g of type string and have it point to a new string on the heap, hello. We're creating another variable h of type string and copying the pointer from g, so now g and h are pointing to the same object on the heap. Since strings are immutable, we can't reach into this object and make changes to it. If we want to manipulate what h and g are pointing at, we have to create a new string and move the pointer. We have h point at a new object, goodbye, which is going to be a completely different object on the heap. So now g and h are no longer pointing at the same objects, and the objects have different values. In this Java tutorial, we're going to learn how to check equality of different data types. We'll discuss the different methods and what happens behind the scenes when you use each comparison method with different data. Some key facts to know. Primitive data types can be compared using double equals. For example, if we've got two primitive variables, we can say A double equals B, and that Boolean expression will return either true or false. Using double equals to compare two reference, also known as object type variables, will only check if they are pointing at the same object, not whether if those two objects have equal values. Also, reference, object type variables, can be compared using the equals method. For example, a.equals b. For some classes, this will check if they are pointing at the same object, much like using double equals. In other classes, it will check if they are pointing at equivalent objects, and we'll discuss that more later. Let's start by reviewing the 8 primitive data types in Java: Boolean, char, byte, short, int, long, float, and double. We're going to have some examples in the next part about how to compare values of these data types. So let's write some code. First, we'll declare an int a set it equal to 3, int b equals 3, double c equals 3.0, double d equals 3.0, and then boolean e equals false. We'll execute this code, and we'll see for primitive type variables, all data ends up on the stack. Now let's take a look at some Boolean expressions. We'll start out with a double equals b. This will evaluate to true because the value of a on the stack is the same as the value of b on the stack. Next, we'll look at this Boolean expression, a is not equal to b, which is false because a is in fact equal to b. Next, let's take a look at this expression, c is equal to 3.0, so the value of c on the stack is 3.0, so this is true. Here we're comparing a to d. Now we see a and d are different data types. A is an int, d is a double. However, for this comparison, it will convert a to the double 3.0, and 3.0 is equal to 3.0, so this will evaluate to true. Finally, we have the expression c is equal to e. So we're comparing 3.0 to the Boolean value false. This is going to generate an error because there's no way for the compiler to compare a numerical value to a Boolean value. Now let's move on and talk about comparing objects. We can use double equals to compare two reference object type variables, but this will only tell us if the two variables are pointing at the same object, which is generally not what we want to know. We can also compare two reference object type variables using the equals method. For example, a.equals b. For some classes, the equals method is a shallow comparison. It only checks if the two variables are pointing at the same object, so it works similar to double equals. For other classes, the equals method is a deep comparison, meaning it checks if the data in the two objects are the same. So it's important to know, depending on the object type you are dealing with, is the equals method a deep comparison or is it a shallow comparison? We're going to start by using ArrayLists to do some comparisons. We will learn about how ArrayLists work later, but for now just understand that they are a data type that holds some information. We'll start by declaring an ArrayList, initializing the variable, then adding a couple of values to the ArrayList. So we have our reference variable ABC on the stack, and it's pointing to the ArrayList object on the heap. Next, we're going to declare another ArrayList variable and copy the pointer from the ABC variable. So here we go. So we can see the reference variable ABC and the reference variable DEF are both pointing at the same object on the heap. Now we're going to declare a new reference variable of type ArrayList, GHI. We'll initialize it with a new ArrayList, and then we'll add the same three objects. So here we can see GHI is pointing at an identical object of DEF and ABC. However, the two objects are in different memory locations on the heap. Now let's examine some different ways to compare the values. We're checking ABC double equals DEF. So ABC and DEF are pointing at the same object on the heap, so this expression is going to evaluate to true. Here we're saying ABC double equals GHI. Now, ABC and GHI are pointing at identical objects, however they're in different memory locations on the heap, so this will evaluate to false. For this reason, double equals is usually not a good way to compare objects in Java. Now let's look at using the equals method. For ArrayLists, equals is a deep comparison, meaning it's going to check the contents of the object, not just where they are in memory. So let's look at this one. ABC equals DEF. Well, ABC and DEF are pointing at identical array lists, so this will return true. Now ABC equals GHI. Well, the array list that ABC is pointing at is identical to the array list that GHI is pointing at, so this will also return true. Now let's learn about doing comparisons with arrays. Let's take a look at this code. So here we're declaring a reference variable of array type A and having it point at a new array object. Then we're declaring the variable B and we're copying the pointer from A. Then we're declaring the variable C and having it point at a new object in memory. We'll take a look at it here. So A and B are pointing at the exact same object. C is pointing at an identical object in a different memory location. Now let's look at some Boolean expressions. We see A double equals B. Now arrays are objects, so this is going to check, are they pointing at the same object? So A and B are pointing at the same object, so this will evaluate to true. Now we're saying A double equals C. A and C are pointing at identical objects, but they're not in the same memory location, so it's going to evaluate to false. Now let's look at using the equals method. With arrays, the equals method is a shallow comparison. So it's also going to check, are these variables pointing at the same object? So A equals B, they are pointing at the same object, so this will evaluate to true. And then A equals C, the objects are identical, but they're not the same object in memory, so this will evaluate to false. So now we're going to look, how can you accurately compare the contents of the object with two arrays in Java? The first thing we have to do is, before we declare the class, we have to say import java.util.arrays. Then, when we're ready to compare, we say arrays with a capital A, dot equals, and we have two arguments, which are going to be the variables for the two arrays we want to compare. So this is actually going to check the contents of the array. So A and B, of course, the arrays are the same contents, so this will return true. Here, we're comparing A and C, and A and C are pointing at identical arrays, so arrays dot equals A comma C will also return true. Lastly, we're going to look at comparing strings. There's two ways to declare and initialize strings in Java, and they affect how the data ends up on the heap. The first and most common way is we say string, name of the variable, then set it equal to a string literal. In this case, we place a reference variable on the stack, and then we place the string in a string pool on the heap. Now, we're going to declare string B and also set equal to coffee, and something interesting happens. Before creating a new object, the Java virtual machine checks and sees there's already an equivalent string on the heap. So what it's going to do is create B and have it point at the same value. Now, there's another way we can declare and initialize strings. We can say string, and the name of the variable, equals new string, and then put the string literal in there. In this case, it's going to create individual objects outside of the string pool on the heap. Now let's look at a couple of Boolean expressions. Here, we start with A double equals B. So this is going to check, are A and B pointing at the same object? And in this case, they are, because of the way we declared and initialized A and B. So this will evaluate to true. Now, we declared and initialized C a little bit differently. So when we compare A to C, they are pointing at different objects on the heap, so this Boolean expression will evaluate to false. Now let's take a look at what happens when we use the equals method. With strings, the equals method is a deep comparison. So we're going to check, is A and B pointing at equivalent objects? It's the same object, so of course they're equivalent, and this will return true. Now we do A equals C. So we see A and C are pointing at equivalent objects, even though they are in different memory locations, so this will also return true. Finally, let's take a look at how we could actually use some of these comparisons in code. So here, let's assume A and B are primitive type variables, so we want to compare them using double equals, and not equals. Here, let's assume that C and D are object type variables where the equals method is a deep comparison. So in that case, we want to compare them using the equals method, like C dot equals D. For E and F, we're assuming that they're arrays. So the proper way to compare them is using arrays dot equals and then our two variables that are pointing at arrays. Some final things to remember. We use the double equals to compare primitive data types. Some object types can be accurately compared using the equals method. You have to know, for that particular object type, is it a shallow comparison or a deep comparison? Other objects may have alternative methods to compare their contents, like arrays use arrays.equals. For some objects, there may not be an easy way to compare them, and that was just how the programmers designed them. In this Java tutorial, we're going to learn about the string class. Some important facts to know. Strings are a data type that can hold text. Internally, strings are an array of the primitive type char. The string class has a variety of methods to compare and modify strings. You can look up all the methods in the class online on Oracle's website. Before we get into new string topics, we're going to review how strings are handled in memory. We're going to look at two different ways to declare and initialize string variables. Depending on how we do it, Java will handle them differently in memory. The most common way is to say string, the name of the variable, then set it equal to a string literal like this. In this case, Java will place a variable on the stack and have a pointer pointing at the object on the heap. For strings, it will place them inside a string pool. What this means is that if we declare another string with the same value, Java will simply look in the string pool and see that it's already there, and then have that next variable point at the same memory location. This is different behavior than with most other objects, and it serves to save memory. Now let's look at a second way to declare and initialize string variables. Here we're saying string C equals new string hello. This is more like how we declare and initialize most objects. When we do it this way, Java will create a unique object outside of the string pool. If we do it again this way, even though it's the same value, it's going to create a second object on a different part of the heap. Now let's look at this line of code. For the purpose of this lesson, SOP stands for System Out Print Line. We're checking, does A double equals B? With primitive types, this compares the values that are stored on the stack. However, with object types, double equals checks are the variables pointing to the same location on the heap. The values on the heap may be the same, but if they aren't pointing to the same location, this will return false. In this case, A and B are pointing to the same memory location, so it will return true. Now let's compare it to this line of code. We're checking, are C and D the variables pointing at the same memory location on the heap? They are not, so this will print out false. Even though the data on the heap is the same, the memory locations where the data is stored is different. Because of this, double equals is not a good way to compare objects. In the case of strings, we prefer to use the dot equals method. So A dot equals B compares the data that A and B are pointing to. So this hello is the same value as this hello, so it will be equal. Now C and D, which are pointing to different memory locations, but the data in those memory locations are the same, so the dot equals method in the string class will compare the actual strings at those memory locations, and it will also print out true. Let's look at another way to use the dot equals method in the string class. Here we say A dot equals the string literal hello. A is pointing at a string that says hello, which is equal to the string literal hello, so this will return and then print out the value true. Next, let's change A. We're saying A equals hola. Strings are what's called immutable, which means we can't change the data on the heap. So if we do something like set a equal to Ola, it's going to create a brand new object, and it's going to move the pointer from a to that new object. Let's look at some other examples to see how strings are handled in memory. Here we're declaring a reference variable e and having it point at a new object high. Here we're creating a new reference variable of type string f, and we're copying the pointer from e to f so they're pointing at the same memory location. Now what we're doing is we're creating a new reference variable g of type string and setting it equal to the string literal howdy. Next, we're declaring string h and setting it equal to high with h and I capitalized. Here we're checking, does e dot equals f? E and f are pointing at the same memory location, though for the dot equals method that doesn't matter. What matters is they are both pointing to an object that are equivalent to each other. So this returns and prints out true. Here we're checking e and h. Even though e and h are both pointing at an object that says high, Java considers different capitalization to be unequal. Here we check e equals ignored case h. So in this case, e and h are equal because if we ignore capitalization issues, these are the same words that they are pointing at. Here we are using the dot length method. The dot length method checks the number of characters in the string that a reference variable is pointing at. So g is pointing at howdy, which is 1, 2, 3, 4, 5 characters. The next method we're going to look at is the substring method. What this does is this takes a part of the string and returns the substring. In the case where we have one argument, it starts at this index and then returns everything from this index to the end. Like arrays, strings are zero indexed. So g is pointing at howdy, index 0, 1, 2. It starts at 2 and goes to the end, so it returns a substring wdy. There's a second version of the substring class that has two parameters, so we need to provide it with two arguments. In this case, the first argument is where we want to start, and the second one is where we want to stop. However, you must be very careful because the first index is inclusive while the second one is exclusive. So we will start at index 1, but we will end 1 before index 4. So we see g substring, index 1, 2, 3. It does not include index 4. Finally, let's look at the compare to method. What this does is it looks at the strings that h and e are pointing at and converts them to Unicode numerical values. Then it compares it and will return a 0 if they have the same Unicode values, or it will return a positive or negative number. This is very useful if we want to create a sorting algorithm that organizes strings lexicographically. If we want to organize strings alphabetically, it's more useful to use compare to ignore case. Finally, let's look at a couple of examples of how we might use these methods. Here, I'm taking the length of the string h is pointing at, and I'm storing it in an int value I. Here, we are checking if e, which is currently pointing at a string high, equals the string literal high. In this case, if this returns true, we are going to have it print out e equals high to the console. In this lesson, we're going to talk about the difference between objects versus classes in Java. Now, you'll sometimes hear me, instead of using the term objects, you'll hear me use the term instances of classes or instances. And I'm using that as an alternative for objects. Okay, so example of languages that use an object-oriented paradigm: Java, C++, C#, and Python. There's many more, but these are four major ones. So what is an object? In object-oriented programming, objects have the following. They have states, and we do that with fields in Java, and they have behaviors, and we do that with methods in Java. So let's take an example of a real-world object that we might want to represent in programming. So this dog has states: color, is it awake, and its age. And the dog also has behaviors like bark, run, and eat. The states would be represented by fields, the behaviors would be represented by methods. So what is a class? A class is a blueprint or a template for an object. So I use this picture as an example. This is not an actual car, but it's a blueprint or a template for the car. Now, there are certain behaviors in Java that we can access without creating the object. We can do it simply from the class. And these are static methods in Java. And we know they're static methods because they have the word static there. For example, we can rotate the wheel in this blueprint. We can open the hood in this blueprint. That's why these are static methods. We don't need to create the actual car to use them, though we could use them on an actual car. Now, non-static methods. These are behaviors that we can only access from an object. In Java, we call these non-static methods, and they don't have the word static, so that lets us know they're non-static methods. If we want to turn on the engine, we actually have to create a car from the blueprint. We have to create an instance of the class. Same thing with drive. We have to create an instance of the class and apply drive method to it. Alright, so let's talk about class variables. Now these are static fields, and these are states that belong to the class. In Java, we call these class variables, or sometimes static fields. Understand, if you change a class variable anywhere, you change it everywhere. So if we change the wheel size anywhere in any instance, or the class itself, it'll change all instances. So if we change the wheel size in one place, since the wheel size belongs to the class, it changes it everywhere. Same thing with vehicle type. We change it one place, it gets changed everywhere. We also have instance variables. And these instance variables, also called non-static fields, we can't give them an actual value, or they don't have an actual value, until we create an instance of the class. So we can lay out what their value will be, but we can't access that value until we create the instance. So in Java, we call these instance variables, also known as non-static fields. Only an object may have a value for the instance variables, though like I said, we can set out what the value will become in the class. And changing the values in one object does not affect other objects. So here's an example of some instance variables. They don't have the word static, so we know they're instance variables. Color and license plate. And if we change these in one place, they only change for that particular instance. So additional notes. A static method can only access class variables. A non-static method can access class variables or instance variables. And you notice we had the private keyword on our fields. What that does is that makes it so the fields can't directly be accessed by other classes. That helps us prevent bugs. Here's some sample class code. So for our class Audi A8, we've got private static int wheel size. This is a class variable. It belongs to the class. This is an instance variable. It belongs to the instance. Private string color. Then we have some methods. I didn't actually put the code inside it to save space. Private static void rotate wheel. This is a static method, so we don't have to create an instance to use this. We've got public void turn on engine. This is a non-static method. We can only call this from an instance. And then there's going to be some getter and setter methods that are not shown. Alright, here's some more sample code about how we might use the Audi A8 class. So we've got our main method. Here, I'm calling rotate wheel. I'm calling it from the class. This is legal to do because rotate wheel is a static method. Here, I'm declaring a new variable called Jane's car. The variable is of type Audi A8, and we're creating a new object, and Jane's car has a pointer that's pointing at that new object. Then we're calling Jane's car rotate wheel. Even though rotate wheel is a static method, we can still call it from an instance. And then we're also calling start engine. Start engine is a non-static method, so we can only call this from an instance. Some additional notes. The private static int wheel size is a class variable. Private string color is an instance variable, and we know that because static means it's a class variable. No mention of static means it's an instance variable. If we make a change to wheel size, since it is a class variable, it will change the value everywhere. And if we make a change to color, which is an instance variable, it will only change the value in one instance. Today we're going to talk about static fields. We're going to talk about getter methods and setter methods. Now before we start, let's look at the two classes I have, the student class and the classroom class. Student class, we're going to create instances of the student class to hold individual student data. Classroom, we're going to have our main method and we're going to create some students inside it. Okay, so let's look at this first field. Now the great thing about fields is they are valid throughout all the methods in the class. So unlike a local variable that we might create inside a method and would be destroyed when the method ends, these fields are valid throughout all the methods in the entire class. Now let's look at these commands. This says private. What this means is we can't directly access this variable outside of the student class. So if we want to access it from the classroom, we have to have a getter and or a setter method. Static means it belongs to the class itself. So we call the static fields, we also call them class variables because they belong to the class. This is going to be a string, and I'm naming it mascot. Now you notice I haven't initialized it, and of course we always have to initialize a local variable before we use it. But fields, if we don't initialize them, they'll be initialized automatically. For example, since this is a string, which is an object fields always default to null. On the other hand, this is an int fields always default to 0. Now we are more than welcome to initialize a field if we want. This one I've initialized to 123.4. This is perfectly legal. Now this is something that students do sometimes that's not legal. We've declared it, which is fine, but then we try to initialize it on the next line. And we can't use a command like this outside of a method. If we wanted to initialize class code 2, we would have had to do it on the same line like we did class code 1. Okay, so we want to access these inside the student class in any method, no problem. But let's say we wanted to access them from another class. Since these are private, we have to use what's called getter and setter methods. Now, you notice I made this one public, and that's because we want this method to be accessed from outside of the student class. If we made this private, it wouldn't be very useful as a getter method because it would only be accessible inside the student class. Now I made this a static method, and that means that we can use it to be accessed from either the class itself or from an instance of the class. And we'll talk about this a little more later. Also, since this is a static method, we can only access static fields. If we had non-static fields, we couldn't access it with a static method. All right, it has to return something, because if it's going to get something, it's got to be able to return it. In this case, we want to return a string. We're calling the method getMascot, and this is again an example of a getter method. You also may hear them called accessor method. It means the same thing. And all this is going to do is this is going to return the data inside the mascot string. It's actually going to return the pointer to the memory location. Okay, this is a setter method. This is if we want to change it. Again, we got to make it public so it can be used from other classes. We're making it static. Static methods, of course, can only access static fields. If it were a non-static method, it could access either static or non-static fields. Void. In this case, we don't want to return anything. More often than not, setter methods don't return anything because they just do something. So we're going to call it setMascot. We have to have a parameter because we got to pass the value we want to change it to. By the way, setter methods are also called mutator methods. Now what we're doing here is we're saying we want to change the field mascot to whatever is in new mascot. Sometimes students get this mixed up, so they end up changing the parameter to what was inside the field. So we're changing mascot and we're putting the value that is inside new mascot into mascot. And again, this is going to be a pointer to a memory location that's going to be a string on the heap. Okay, so let's look about how we can use this. So we have another class called classroom. Now here I just gave an example of a call to getMascot. This is not legal because it's assuming that getMascot is inside classroom because we haven't said otherwise. Since there's no method inside classroom called getMascot, it's going to say we can't find the method. So how can we do it? Well, what we can do is, since these are static fields, we can either call it from the name of the class, which is student, or we can call it from an instance of the class. So I'm going to start by doing it from the name of the class. So I'm saying call getMascot from the student class. Now, as we discussed, this is going to be null because this is automatically, by default, set to null. Then I'm using the setter method. So I'm saying in the student class, call the setMascot method, and I'm passing this argument here, Duke, which will go to this parameter here, new mascot, and it'll be used to change the field. And then I'm printing out the value again, which will now be Duke. Now here I'm creating a new instance of the class student. So this is an object. I'm calling it Jennifer, and I'm making another one. I'm calling it James. Really, truly, since these are variables, they should be in lower camel case. So let's just change that there. Okay, so I've made these new instances of the class, or we could call them objects. Same thing. I'm saying Jennifer.setMascot to new Duke. Now, since mascot is a static field, this will change it in every instance and even the class itself. So now every mascot is going to be new Duke. So now when I'm using getMascot from James, or even if I wanted to do getMascot from the class itself, it would be new Duke. So for certain things, static fields are great. If when we change one, we want it to change everywhere, a static field is great. Something like student ID, this is not a good choice for a static field because we want James and Jennifer and everybody else to have their own student ID. So that is discussion of static fields, getter methods, and setter methods. Later on, we will learn about non-static fields, and we will learn how to access them using non-static methods. In this lesson, we're going to talk about the difference between static methods and non-static methods. For this example, we've got two classes, one called book and another called library. Now we also have two fields in the book example. One is a static field, also known as a class variable. The other is a non-static field, also known as an instance variable. We're going to talk about the differences between class variables and instance variables in the next video. For now, we're just going to talk about how they can be accessed by static versus non-static methods. Now, a static field can be accessed by either a static method or a non-static method. Now, in this case, I chose to write my getter method using a static method, but I could have done it with a non-static method too. Now, on the other hand, my non-static field, my instance variable, I have to use a non-static method to access it. So my getter method for title had to be non-static. Okay, so we've got our examples there. Now let's look at library. Now I'm making an instance of a class, an instance of the book class, and an instance of a class is also called an object, called Mythical Man Month. So I'm creating a new book with the variable name Mythical Man Month, and I say equals new book. So I'm creating an instance of that. Now here, I'm calling the getPublisher method from the name of the class itself. This is legal to do if this method is static. I couldn't do this if this method was non-static. Now here, I am calling getPublisher, and I'm calling it from the instance of the class. This is also legal with a static method. Now let's look down here. Here I'm trying to call getTitle. GetTitle is a non-static method. This is not legal to call a non-static method from the name of the class itself. On the other hand, it is legal to call a non-static method from the instance of the class or the object that I created. Now let's talk about calling static methods and non-static methods if they're in the same class. So in the library class, we have the main method and we have the say hello world method. So main is always going to be a static method. Now I can't call a non-static method directly from a static method. So this is not legal. I can't call say hello world directly from main because say hello world is non-static and main is static. On the other hand, if I make an instance of a class, like I made an instance of the library class, then I can call this non-static method from the instance. So, to review, a static method can access a static field only. A non-static method can access either a static field or a non-static field. A static method can be called either from the class itself or from the instance of the class. A non-static method can only be called from an instance of the class. And if we want to call a method in the same class from a static field, and the method we are calling is non-static, we can't just call it directly. We have to create an instance of the class we're in, library, then we have to call the non-static method from the instance that we just created. In this Java tutorial, we are going to discuss what null means and what it means when a reference variable is set to null. 4 important facts to know about null. First, null can be thought of as a reference that doesn't point at an object. Second, a variable that is initialized as null is different than a variable that is uninitialized. Third, static methods can be called from a variable initialized as null. Fourth, you can write code to check if a variable is null before you try to use it. We're going to write some code. All the variables here will be local variables. We start by declaring a variable x of type int_array, and we're going to leave it uninitialized. If this were a field, it would automatically initialize itself to null if we hadn't done anything. Next, we're declaring a variable y of type int_array, and we're explicitly initializing it to null. We can see there's a pointer, but it doesn't point at an actual object. Third, we are declaring a variable z and setting it to point at a new object we created on the heap. Let's look what happens when we try to access these variables. Here, we're trying to reach into the variable that x is pointing at and change index 1 to 9. This will cause a compile time error because our Java compiler knows that x isn't even pointing at anything. Next, we are trying to reach into the object y is pointing at and change index 1 equal to 9. The compiler will accept this. However, when we are running it, we will receive a crash of a null pointer exception because there is no object to actually reach into and change. Finally, we are reaching into the object z is pointing at and changing index 1 equal to 9. There is a pointer and there is an object it's pointing at, so index 1 will change to 9. Let's look at this class we're going to use for our next example. We have public class cat, we have a static field fall, and we have a non-static field meow. We're going to write some more code with local variables. Here we are declaring a variable whiskers of type cat and leaving it uninitialized. Next, we are declaring a variable catzilla of type cat and setting it equal to null. So there is a pointer, but no object that it is pointing to. Third, we are declaring a variable Claudia of type cat and having it point to a new object on the heap that we just created. Let's see what happens when we try to call methods from these variables. First, we try to call fall and meow from whiskers. This won't work because whiskers is not initialized at all, so we can't call any method either static or non-static. Next, we're going to try to call fall and meow from catzilla. Catzilla is initialized to null. Since fall is a static method that belongs to the class, we can actually call it from a variable defined as null. On the other hand, meow is a non-static method, so we can't call it from a variable defined as null. Finally, we have our variable Claudia, which is pointing at a cat object. In this case, we can call either fall or meow. Next, let's look at an example where having a variable set to null could get us into trouble. Here we have a method petCat that has a parameter of type cat named thisCat. On this line, it's going to try to call the non-static method meow from the variable thisCat. If this cat is set to null, we're going to get a crash and a null pointer exception. Let's look up at our main method. Here we have a cat variable, kitCat, that's pointing to an instance of cat. We're calling petCat and passing it the reference to that cat object. This will work fine because this cat will be pointing at the same object as kitCat, and it will be able to call the non-static method meow. Now let's look at this example where kitCat is set to null. We're going to pass the null pointer to the parameter this cat, and when we call meow from this cat, we're going to crash with a null pointer exception. Sometimes on tests, we're guaranteed that the parameters will not have a null value. In this case, we don't have to worry about something like this happening. However, if this is not specified, we need a check to make sure our parameter isn't set to null before we try to call a non-static method from it. This code checks if the variable this cat is not equal to null. If it's not equal to null, we're going to do the code and call meow from the object this cat is pointing at. If this cat is equal to null, we're going to go to else and just say there is no cat to pet. That way we won't get a crash. In this Java tutorial, we're going to learn about scope and lifetime of variables in memory. What is scope and lifetime? Scope determines where in a program that a variable can be accessed. Lifetime determines when a variable or object is created and when it is destroyed in memory. The scope and lifetime of a variable is determined by where it is declared, not where it is initialized. Sometimes we declare and initialize variables on the same line, sometimes we don't. Let's take a look at this class. We have our main method here, and we have 4 variables, a, b, c, and d. A, b, c, and d are all local variables because they are local to this method. Int a is declared here at the top of the method, and its scope is anywhere inside this method, and its lifetime is from where it is declared until the end of the method. Int b is declared inside this block of code here. So it's created when this block of code runs, and it's destroyed when this block of code completes. Here we have int c that is declared as part of this for loop. C is declared when we begin the for loop, and it is not destroyed until all cycles of the for loop are complete. Int d is created inside this block of code that's part of the for loop. Int d is created every time we run a cycle of the for loop, and is destroyed every time we end that cycle. Then it's recreated again when we run the cycle again. Let's take a look at this other class. We have a main method and we have another method. We're going to start tracing it out. So we're going to declare a, then initialize a. So that puts a and its value 3 on the stack here. Now we're going to call another method, and when another method runs, it'll run this code inside. Notice a becomes grayed out. That's because a is out of scope. It's not available in another method, since local variables are only available in the methods where they are created. However, it still exists on the stack, so the data's there, it's just not accessible right here. We finish up another method, and then we're back to our main method. Now we see a is now back in scope. Finally, we end the main method, so a is destroyed and removed from the stack. Next, let's take a look at this class. We'll start by looking at method 2. Method 2 has a parameter called name. Parameters are variables that are defined in the method declaration. We have to pass a value to them anytime we call the method. Parameters are created when the method runs, and their scope is anywhere inside the method. Their lifetime begins when the method is first called and ends when the method call is complete. Now let's take a look at this class variable here. Class variables are also known as static fields, and we declare them as static when we create the variables. Class variables are created the first time we use the class or we create an instance of the class. Class variables are accessible in all static or non-static methods in the entire class. The class and all instances of the class share one value for each class variable. So if you change it one place, you change the value everywhere. Now let's take a look at this instance variable here. Instance variables, which are also known as non-static fields, do not have the word static in their declaration. There is a different copy of every instance variable in every instance that we create of a class. So if we create 5 instances of the scope and lifetime class, there'll be 5 separate copies of the B instance variable, and they may each have their own values. Instance variables are created when an instance of the class is created and destroyed when that instance is destroyed. They are only accessible in non-static methods. So we can tell this is a non-static method because it doesn't have this word static there. This method is static, so we can't access instance variables. If you want to learn more about class variables and instance variables, please click on the link in the upper right-hand corner of the screen. A very important thing to remember is that when making getter and setter methods for non-static fields, also known as instance variables, you must use non-static methods. Overloaded methods are methods that have the same name in the same class. 3 important things to know about overloading methods. First, overloaded methods must have exactly the same name. Second, overloaded methods must have different number and/or types of parameters. Third, constructors can also be overloaded. We'll talk about what constructors are and how they work a little later. Let's talk about the things that overloaded methods can't have different, what they can have different, and what they must have different. Overloaded methods can't have different method names. Occasionally a programmer will make an error and they will unintentionally give 2 methods different names. The methods will not be overloaded in this case. Overloaded methods can have different return types from each other. Overloaded methods can have different visibility. One could be public, one could be private. Overloaded methods could have different static or non-static values. Finally, overloaded methods could have different parameter names. The Java compiler needs to know which method is being called, so one of the 3 things must be different. First, the number of parameters, or the type of parameters, or the order of the type of parameters. For example, one method could have a string followed by an int, the other could have an int followed by a string. Let's look at some examples. We have 3 overloaded methods here. Output answer has no parameters. This output answer has 1 int parameter. This output answer has 2 int parameters. When we call output answer from the main method, we have 1 int argument. The compiler will use this to match it up to the appropriate method. Here it is. Let's look at another example. We have 3 versions of calculate answer. The first one has 1 int parameter. The second one has 1 double parameter. The third one has 1 string parameter. When we call calculate answer, we have 1 double argument. The compiler will use this to match it up to the correct version of calculate answer right here. Let's look at a third example. We have 2 different versions of compute answer. The first one has an int followed by a double. The second one has a double followed by an int. This call to compute answer will look for one that has a double followed by an int. Right here. Here's an example of 2 overloaded methods that have a lot of differences. First, one is public, the other is private. The first is static, the second is non-static. The first has the void return, the second has an int return. And finally, The first has a parameter A, the second has a parameter Z. This is all fine, however, there's a problem. Both have one Boolean parameter. This means when we call solve for answer with one Boolean argument, the compiler won't know which version of solve for answer we want. Let's correct this. The second one we're going to change from Boolean to int. Now we have one solve for answer with a Boolean parameter and another with an int parameter. Now when we call solve for answer with one Boolean argument, it knows which one to go to. In this Java tutorial, we are going to start learning about inheritance. Part 1, we will discuss inheriting methods. 5 important things to know for this lesson. 1. A class that it inherits is called a subclass. 2. A class that is inherited from is called a superclass. 3. Subclasses are in an is-a relationship with their superclass. We'll discuss this more later. 4. A class can have many subclasses, but only one superclass. And 5. Anything with a private modifier is not inherited, but can be indirectly accessed. Here we have an example of a worker class. Worker class does not explicitly extend anything, so it is not explicitly a subclass. However, implicitly, it extends object, so is a subclass of the Java object class. This class has 2 methods. 1, do work, and 2, earn minimum wage. Do work is a public method. That means 2 important things. 1, it will be inherited to subclasses, and 2, it can be directly accessed from other classes. Earn minimum wage is a private method. That means 2 things. 1, it will not be inherited to subclasses, and 2, it can't be directly accessed from other classes. Our next class is tradesperson. Tradesperson is a subclass of worker. Tradesperson adds a new method called do skilled work. So, tradesperson will inherit do work, and it will not inherit earn minimum wage because it is private, and tradesperson will add a new method, do skilled work. Our third class is carpenter. Carpenter is a subclass of tradesperson. So carpenter will indirectly inherit do work, it will directly inherit do skilled work, and it will add its own method, do woodwork, because carpenters have the additional skill of being able to do woodwork. So here's a map of what our relationship looks like. Worker is a object, tradesperson is a worker, and carpenter is a tradesperson. Let's take a look at a new class, worksite. So we've declared a variable Alex that is a worker type of variable, and we've initialized it with a new instance of the worker class. When we call Alex earn minimum wage, this is not legal. Since we are trying to call earn minimum wage from the worksite class, we can't do this because earn minimum wage is private. Earn minimum wage can only be called from another method in the worker class. Now we are trying to call do work from Alex, and of course Alex is an instance of the worker class. This is legal because do work is public, which means we can directly access it from another class, in this case worksite. Now what's interesting here is our output will actually be does unskilled work and earns minimum wage. Because even though earn minimum wage is private, we can call do work from worksite, and then do work calls earn minimum wage. So indirectly here, we are calling a private method earn minimum wage. Let's look at this next class, worksite 2. We've got a worker, Alex, and initializing it with a new worker, tradesperson, Barbara, and initializing it with a new tradesperson, and carpenter, Carol, and initializing it with a new carpenter. We call do work from Alex. This is legal because do work is a method inside a worker class, and Alex points to an instance of the worker class. This is also legal. Do work is inherited from the worker class because tradesperson is a worker and thus inherits all public methods. Carol is a variable of type carpenter and initialized with an instance of the carpenter class. It is legal for Carol to call the do work method because the Carol variable, inherits do work from tradesperson, which inherited it from worker. And let's look at a third and final class, worksite. We've got worker Alex again, and initialize it with a new worker, tradesperson Barbara, the variable Barbara, and initialize it with a new instance of the tradesperson class, and carpenter Carol variable we initialize with a new instance of the carpenter class. This is illegal because a superclass cannot inherit from a subclass. Only a subclass can inherit from a superclass. So our worker class does not inherit from its subclass carpenter. Same here. We have the Barbara variable, which is a tradesperson, and that does not inherit from its subclass carpenter. We call Carol the do woodwork method. This is legal. The Carol variable points to an instance of the carpenter class, and the carpenter class contains the method do woodwork. In this Java tutorial, we are going to continue talking about inheritance. Specifically, we are going to talk about overriding methods. 4 important things to know about overriding for this lesson. First, overriding replaces a method in the superclass with a different version in the subclass. 2. Only non-static methods can be overridden. 3. There is something similar called hiding that can be done with static methods. And 4. Private methods can't be overridden. Let's look at these 3 classes that we've written a little differently in this lesson. We've got the worker class, the tradeperson class which extends worker, and the carpenter class which extends tradesperson. So tradesperson is a subclass of worker, carpenter is a subclass of tradesperson. Our do work method is public, so we can override it in a subclass. If we don't override it, it would simply be inherited. Earn wage is private, so it will not be inherited and it may not be overridden in a subclass. Here in tradesperson, we've overridden do work, so it has a little bit of a different behavior that's more appropriate for a tradesperson. We were not able to override earn wage, so to get different behavior, we had to create a different method. This one we called earn union wage. In carpenter, we again overrode do work. If we haven't overridden do work in carpenter, it would have inherited the do work from tradesperson. Again, we couldn't override earn union wage or earn wage, so we had to create a new one called earn carpenter's union wage. So let's look at this map of how these classes are related. We have the Java object class, which is going to be a superclass of worker. Then we have tradesperson, which is a subclass of worker. Then we have carpenter, which is a subclass of tradesperson. Let's look at this class worksite, where we create some instances and then call them. We're going to start by looking at the class worker. Line 5 in worksite, we declare a variable Albert of type worker, then initialize it with a new instance of the worker class. We call the doWork method from the Albert instance of worker. So it'll go up here, it'll system out print line do unskilled work, then it will call earn wage method, which outputs earn minimum wage. Got our output right here. Next, let's look at tradesperson Bob equals new tradesperson. So we call do work from the instance in the variable Bob. It goes to the overridden version of do work, which says do skilled work, calls earn union wage, and then earn union wage outputs earn union wage. Finally, we're going to look at line 7. We declare a new variable, Cynthia, of type carpenter, and initialize that variable with a new instance of the carpenter class. We call the doWork method from the Cynthia variable. doWork outputs does woodwork and calls the method earn carpenter union wage, so then outputs earn carpenter's union wage. If we do not override a method in a class, the most recently overridden version will be inherited from a superclass. In this Java tutorial, we are going to continue talking about inheritance. Specifically, we are going to talk about using the super keyword to call methods in the superclass. Some important facts about using the super keyword. We can use the super keyword to call methods in a superclass that have been overridden in the subclass. Second, super can also be used in a constructor to call a constructor in the superclass. We'll talk about this second use when we cover constructors later on. We have two classes we're going to look at here. Our first class is car. Here, we define a new method applyBrakes. Here, we define another method in car, checkSurroundings. Self-driving car is a subclass of car. Here, instead of inheriting applyBrakes from the superclass, we override it. Here, instead of inheriting checkSurroundings from the superclass, we override it. Emergency override is a unique method declared in self-driving car. Here's a map showing the relationship between the classes. Object is a superclass of car. Car is a superclass of self-driving car. Here we have a class highway with a main method. On line 5, we create a variable of type car and initialize it with a new instance of the car class. On line 6, we declare a variable Tesla X of type self-driving car and initialize it with a new instance of self-driving car. On line 8, we call the applyBrakes method from the variable Ford Mustang, which is pointing at an instance of the car class. So up here, call applyBrakes. We output to the console, driver applies brakes. We call on line 6 checkSurroundings, and then checkSurroundings outputs to the console, driver checks surroundings. Let's look at a slightly different version of the highway class. In this one, we call applyBrakes from the variable Tesla X. Tesla X points to an instance of self-driving car. So we are going to call the overridden method applyBrakes in the class self-driving car. On line 5, it outputs computer applies brakes. On line 6, it calls the method checkSurroundings. And here on line 11, it outputs to the console computer checks surroundings. Let's look at a little more complicated example that people often get confused over. Here, we are calling emergency override from the variable Tesla X. On line 16, it outputs to the console driver takes control. On line 17, it calls from the superclass the original applyBrakes. So we're up in the car class here. On line 5, the car class outputs driver applies brakes. This is the point where people usually get confused. They expect the call to check surroundings is going to call the method in the superclass car. However, since Tesla X is an instance of self-driving car, check surroundings is going to call the most recently overridden version of check surroundings. So it's going to call the version in self-driving car even though it's being called from the superclass. This only happens because Tesla X is an instance of self-driving car and check surroundings has been overridden in self-driving car. So now computer check surroundings. In this Java tutorial, we are going to continue talking about inheritance. Specifically, we're going to talk about accessing private fields in a superclass from a subclass. Two important facts to know. First, we cannot directly access private fields in a superclass from a subclass. Second, we can, however, indirectly access them if there are getter and setter methods in the superclass. Let's take a look at these two classes here, animal and bird. Animal has a private field, num of legs. Since num of legs is private, it can't be inherited to a subclass and can't be accessed outside the animal class. In our subclass bird, we have another private field, feather color, which also can't be inherited and can't be accessed outside the bird class. We have a method in the bird class, report stats. Let's look at it line by line. First, line 7, we output the string literal feather color and then concatenate it with a variable feather color. This is legal. Even though feather color is private, the method report stats is inside the same class as the variable feather color. On the other hand, we look at line 8, where we output the string literal legs and concatenate it with the variable num of legs. Even though bird is a subclass of animal, num of legs is private in animal. That means it cannot be inherited and we cannot directly access it here. Let's see what we can do to make this work. First, we're going to make some changes to the animal class. We create a getter method and a setter method that are both public. We can access these getter methods and setter methods outside of the animal class, so we can have indirect access to the field num of legs. Second, in the animal class, instead of trying to directly access the variable num of legs, we are going to use the getter method getNum of legs. Part 1 of our lesson on constructors in Java. So first, what is a constructor? Well, it's important to understand that constructor is activated only when you create an instance of a class. If you run a main method in a class, or you access a static method from the class itself, that does not make a constructor. Only when we create an object, also called an instance of a class, does the constructor run. Second, a constructor behaves much like a non-static method. Third, constructors are used to set up a new object after the object has been created. So let's look at this example. We've got a class robot and a class space station. We have a class variable, fuel source, and an instance variable name. And we have our constructor here. A constructor will have the word public, then the name of the class, then parentheses that may have nothing inside or may have parameters. So the first thing that happens is we set the field fuel source equal to electricity. The next thing we're doing in this example is calling a method. We can call a method from constructors. Random name. So what does random name do in this case? It just generates a random number from 1 to 3 and sets the name field to either Bender, HAL 9000, or Gort based on whether this is 1, 2, or 3. Okay, let's look over at space station. In our main method, we declare a variable of type robot called 1, then we create a new instance of robot. So we'll set fuel source equal to electricity, and we'll generate a random name and put it in the name field. Same thing with our variable 2 and our variable 3. Next, let's look at the situation where we have overloaded constructors. What overloaded constructors are is we have 2 or more constructors, and the compiler differentiates them because they have different parameters. Now, In our example here, under factory, we create a new variable called 1 of type robot2, and then we create a new instance of robot2 and we pass the string r2d2. Now the compiler looks and says, okay, we've got one argument and it's a string, so we have to find a constructor that has one argument that's a string. And here's a constructor right here. So what it does is it says fuel source is equal to electricity, and then it takes the string that we passed in new name and sets our name field equal to the value of the new name parameter. Now let's look at this second one. We've got a variable named 2 of type robot2. We make a new instance of robot2, but we have no arguments here, so it's going to go to the constructor with no parameters. Now this is an example of using the this command. And what that does is, in this situation, this is going to call another constructor. So it's looking for a constructor that has one string parameter. So it goes to this one. It passes the string wall-e, so it'll set fuel source equal electricity, and it'll set name equal to new name, which happened to equal wall-e in this case. So let's look at another example where we can run into a problem overloading constructors. Okay, so now we have a class called robot confused and we have a class called alien planet. So we've got our two fields and we've got two constructors. Now these constructors both have two strings. The strings have different names in the parameters, but it's two strings. This is a problem because when we want to create an instance, we're passing two strings. Our compiler doesn't know, do we want to use this constructor or this constructor? It could legitimately be either. So robot confused won't even build because when the compiler tries to create an instance, it's not going to be able to know which constructor we want to use. In this Java tutorial, we are going to continue talking about constructors. Specifically, how constructors can call constructors in the same class, or constructors can call a constructor in their superclass. 4 important things to know about constructors for this lesson. 1. Every class must have a constructor. 2. Every constructor must call a constructor in its superclass. 3. Constructors are never inherited. And 4. The Java compiler will sometimes write missing constructor code for us. We're going to discuss more about when and how the Java compiler writes missing constructor code for us. Let's look at this example of the vehicle class. The vehicle class doesn't explicitly extend any other class. However, even though it doesn't explicitly extend another class, implicitly it extends the Java object class. While I've never seen it written this way, technically you can write extends object. Let's look at the 3 constructors. The first one has no parameters. The first line calls a no parameter constructor in the superclass. Object has a no parameter constructor, so this will work. If we are going to explicitly call a no parameter constructor in the superclass, it must be the first line in the constructor. Next, we have another constructor. This one does not directly call a constructor in the superclass. What it does is it calls another constructor in the same class. So this, followed by parentheses, means we are calling another constructor in the same class. There are no arguments here, so it will call the no parameter constructor. This no parameter constructor then calls the constructor in the superclass. So indirectly, this constructor is calling the constructor in the superclass. Let's look at this last constructor. Here we aren't calling the constructor in the superclass at all. In this instance, the Java compiler will insert a call for us to call the constructor in the superclass. In this case, the constructor will always call the no parameter constructor in the superclass. So what if there isn't a constructor at all? In this vehicle class, we have no constructor at all. The Java compiler will automatically insert a simple constructor for us. That simple constructor will call the no parameter constructor in the superclass. Remember, this only works if the superclass has a no parameter constructor. Let's look at these three classes. We've got a vehicle class, an airplane class, and an F-16. Vehicle, of course, implicitly extends object. Here, we don't have a call to the constructor and the superclass. So, Java is going to insert this for us. Let's look at the airplane class and its constructor. This is going to cause problems. We have explicitly called a no-parameter constructor in the superclass, but as we can see, there is no no-parameter constructor in the superclass. We're going to have to change this and rewrite it. So now we've got a string and an int argument, which matches a constructor in the superclass that has a string and an int. Let's look at the F-16 class. This one has no constructor at all. The Java compiler is going to insert a constructor for us. And here, it inserts a very simple constructor. This simple constructor is going to call the no parameter constructor in the superclass. The constructor in the superclass is no parameters, so this is going to work. Remember, Java only creates a simple no parameter constructor for us if there aren't any other constructors in the class. In this Java tutorial, we are going to continue looking at constructors. Specifically, we're going to look at a couple of sample classes, examine their constructors, and trace through the creation of several objects. We remember from previous lessons that every constructor must call a constructor in the superclass. We'll also learn in this lesson that we often use this call to pass up important information to the superclass. Let's look at this sample class Ghost. It's got two instance variables, string, color, and Boolean is scary. It's got a constructor. We don't explicitly call constructor in the superclass, so the compiler will implicitly make a call to the no parameter constructor in the superclass. This only works if there is a no parameter constructor in the superclass, but Ghost is implicitly a subclass of the Java object class. The Java object class does have a no parameter constructor, so this line of code will work. We also notice we've got a field color and a parameter color with the same name, and a field is scary and a parameter is scary with the same name. If we don't specify which one we're referring to when there's a parameter and a field, or a local variable and a field of the same name, it will assume that we are talking about either the local variable or the parameter instead of the field. We can use the this command in either constructors or non-static methods to specify that we are talking about the field. Next, we're going to take a look at a subclass of Ghost, Slimer. Slimer adds its own instance variable, Boolean is hungry. It has its own constructor. The constructor starts by passing up the string literal green. All Slimers are green, so we simply pass up green. And it passes the value of the parameter is scary up to the constructor in the superclass Ghost. Finally, it takes the parameter is hungry and uses that to set the field is hungry. We're going to write some code now. For the purpose of this tutorial, we will assume that this code is in a main method somewhere. We'll start by declaring a reference variable Sam of type Ghost. Next, we will initialize Sam with a new instance of Ghost, and we will pass the arguments white and true to the parameters in the Ghost constructor. The first thing the constructor does is call the no parameter constructor in the superclass, which is the Java object class. We don't need to worry about what the constructor in the Java object class does. The next thing we do is we set the field color equal to the parameter color. In this case, the argument white went to the parameter color, which then went to the field color. So now it ends up in the object. Next, we will set the field is scary to the value of the parameter is scary, which was true, and ends up in the object. So now we've got an instance of the class Ghost on the heap. Next, let's create an instance of a Slimer. We start by declaring a reference variable Sue of type Slimer. Next, we initialize Sue as a new Slimer and pass the arguments true and false, which go to the parameters is hungry and is scary in the Slimer class. The first thing we do is we pass up the string literal green and the value is scary that was passed from the arguments. When we get up to the superclasses constructor, the first thing we do is we call the constructor in the Java object class. Then we set the field color to the parameter color, which was passed up as green. Next, we set the field is scary to the value of the parameter is scary, which was passed up from the subclass, and that value was false. So both those values end up in the object on the heap. We notice we have a line separating the two portions of the object on the heap. This portion has the instance variables for the superclass Ghost. This portion has the instance variable for the subclass Slimer. Now that we've finished with the constructor in Ghost, we can continue back down to finish the constructor in Slimer. So we set the field is hungry to the value of the parameter is hungry, which had a value of true because that's what was passed to us when we created the object. So we can see is hungry is true on the object on the heap. Now we've got two objects. We've got a Ghost object and we've got a Slimer object. We're going to talk about the this keyword in Java. So what is the this keyword? This contains a pointer to whatever object this is currently in. This, even though it acts kind of like a variable, it does not need to be declared. Also, this can only be used in either non-static methods or constructors. So let's look at it. We've got a heap here, and let's say we've just got some random object on the heap, and inside that random object we've got these two variables, string x, which points to another object on the heap, int array y, which points to another object on the heap, and this, which points right back around to the original object. So there's three main uses for this. Number one, to specify a field over another variable of the same name. 2, to call another constructor in the same class. And 3, to pass a copy of a pointer, reference, back to the current class. So let's take a look at these three uses individually. So first, to specify a field. Now I've created a couple of fields. One's static, one's non-static. And then I've created some methods. Now let's look at the printx method. You notice I've got a local variable with the same name as the field. This is legal. However, when we tell it to access x, it is going to give the local variable precedence. Now let's look at another example. Let's say we have a setter method. So we're accepting a parameter x, and again we have a field with the same name. Well, we want to change the field to the parameter's value. So to specify when we're talking about the field, we say this. So we're talking about this object dot x equals the parameter x. Same thing here, y. We're creating a local variable y, and we're saying this y, as in the field, equals y, the local variable. Second use is to call another constructor in the same class. So we've got this first constructor here, then we have this, and we're calling this other constructor here. If we use it in this sense, this must be the first line in the constructor. And the third is to pass a pointer, reference, back to the current object. So we made a random class, we'll call it this keyword 3. The first thing we do in the main method is we created an instance of this keyword 3. We called it anObject, and we set that to equal new keyword 3. So anObject is a new instance of keyword 3. So what happens is we have a new object. Then, since we've created this new object, this also caused this instance variable to be created, which is a different class called SumClass. and the name of the variable is another object, and that points to a new instance of some class. So what happens there is our variable another object points to an instance of some class. Now we're calling method 2 from the instance an object, and we go to method 2, and what this is doing is this is calling a method called SumMethod in the instance another object, and it is passing this, and this being the pointer back to the original object. So we passed it, and this new object created a variable that points right back to the original object. In this lesson, we are going to review objects and references in memory and see how we can apply them to the concept of polymorphism. 3 important things to know. First, when declaring a reference type variable, we specify what type of object it will refer to. Second, when we initialize a reference variable, we give the variable a reference or pointer to an object on the heap. Third, we may create a new object as part of the initialization. Let's write some code. First, we're declaring a variable x of type int array. Next, we are doing 2 things. We are creating a new int array on the heap, and we are putting a reference to that object in the variable x. X itself is the reference variable, the pointer is the reference, and in this case the int array is the object. Let's declare another variable y of type int array. Here we're going to copy the reference from the x variable to the y variable. We can see now both x and y are pointing to the same object on the heap. Here we're doing it all in one line. We are declaring a variable of type int array, we are creating a new object on the heap, and we are putting a reference to the object in Z on the stack. Let's look at this relationship of classes. At the top we have the Java object class. Next we have the animal class, which is a subclass of object. Animal is a object. Next we have dog, which is a subclass of animal. Dog is a animal. Finally, we have sheepdog, which is a subclass of dog. Sheepdog is a dog. Let's write some more code. Here's an example. We have animal Joe equals new animal. Next, we are creating a dog reference variable called Mr. Pickles and setting it equal to a new dog object. Joe is a reference variable of type animal, and it points to an object of type animal. Mr. Pickles is a reference variable of type dog, and it points to an object of type dog. Now, let's look at something interesting we can do with polymorphism. Here, we're declaring a variable spot of type animal, and we're having it refer to a new sheepdog object. This is legal because sheepdog is a subclass of animal. We may have a reference variable refer to an object of a different type as long as the object it refers to is a subclass. So since the reference variable is an animal and the object is a sheepdog, this is perfectly legal. A reference variable of one type can point to an object of a different type if the object is a subclass of the reference variable. So let's look at some examples. If we had a reference variable of animal and an object type of animal, this would be fine. We can always have a reference variable point to an object of the same type. Next, let's look at another example. We have a reference variable animal and an object type dog. This is fine because the object dog is a subclass of the reference variable type animal. Third, we have a dog type reference variable and a sheepdog object. This is again legal because a sheepdog is a subclass of dog. Finally, let's look at this example. We have a reference variable sheepdog and an object dog. This is not legal because dog is not a subclass of sheepdog. In this Java tutorial, we are going to start learning about array lists. Some important facts. Array lists are similar to arrays. However, they are more flexible and they are automatically resized as needed when we add or remove an element. Only objects can be stored in an array list. An array list implements the list interface, and you must import the correct packages before using it. The packages are java.util.ArrayList and java.util.list. However, it's probably easier to just import java.util.star. Let's look at the two ways we can create an array list. The first is to say array list, the data type we want to store in it, and the name of the reference variable. Then, to create the object, we say equals new array list, the type of object we want to store, and open close parentheses followed by a semicolon. The second way is to say list, the type of object we want to store in it, the name of the reference variable, equals new array list, the object type, open and close parentheses followed by a semicolon. In either case, we have a reference variable created on the stack and something that points to an empty array list on the heap. Now let's look about how we can use array lists in more detail. Here we're creating a new instance of an array list with the reference variable pets. We are adding the string dog by using the one-parameter add method. The one-parameter add method adds it to the end of the array list. Next, we are adding a cat. Again, it will add it to the end of the array list on the heap. Here we're using a two-parameter add. This tells us what index we want to add it in and the object we are trying to add. It inserts the object, in this case the string owl, inside the middle of the array list and slides everything else down. Next, we can use the set method. The set method will change the value of the object at the given index. So index 0 will get changed to the string bat. The remove command will remove the object at the given index and slide everything else down to take up the empty space. Here we are using the get method. Get pulls the object out of the specified index. In this case, we are going to output the value of the object retrieved. Here we are getting the value at index 0, but we are storing it into a string. Some more important facts about array lists. The add method with one parameter always returns true. On some test questions, it may be important to know this. The add method with two parameters doesn't return anything ever. We can store primitive types in an array list by placing them inside a wrapper class. In this Java tutorial, we are going to continue learning about array lists. Specifically, we are going to learn how to use wrapper classes so primitive data types can be stored inside array lists. Some important facts. We can encapsulate a primitive data type in a wrapper class so that object can be stored inside an array list. For each primitive type, there is a corresponding object type. For example, the primitive type int to the object type integer, the primitive type double for the wrapper class double, and the primitive type Boolean for the wrapper class Boolean. Java version 5 or later supports autoboxing, so it can easily convert between primitive and object types. Wrapper classes are immutable, like strings. That means we can't change the data on the heap. However, we can make the reference variable point to a new object on the heap. Let's start by creating an array list. We are creating an array list that will hold the object type double. Double with a capital D is a wrapper class to hold the primitive type double with a lowercase d. Here we see we created the variable nums on the stack, and it's pointing to an empty array list on the heap. Next, we're going to look at the old-fashioned way to do this without autoboxing. We're calling the add method, and we're creating a new object of type double, and we are passing the primitive type 3.2 into the constructor for the double class. This will wrap up the primitive 3.2 into an object, and that double object will get added to the array list. We notice that the primitive type is encapsulated in the wrapper class. Next, we're going to look how to get the data out of it. Again, this is the old-fashioned way prior to Java version 5. So we're using the get method to get what's in index 0, and then we're calling the double value method from the double wrapper class to translate it to the double primitive type. Once that returns a double primitive type, we're putting it inside the primitive type variable x. Now the primitive type variable x appears on the stack with the value 3.2. Next, we're going to look at how to do it with autoboxing. Autoboxing means it will automatically convert it from a primitive type to an object type for us. So we just add the primitive type 5.6. It will automatically wrap it inside the wrapper class and place that on the array list on the heap. Next, we're using the get method to retrieve the object at index 1. It will return this object, and then through autoboxing it will be automatically unwrapped to retrieve the primitive type value 5.6 stored inside. That will be placed in the primitive type variable y, which appears on the stack. We can see both ways work. This is without autoboxing. This is with autoboxing. In this Java tutorial on array lists, we are going to learn about traversing an array list. Some important facts to know. We can use either a for loop or a for each loop, also known as an enhanced for loop, to traverse an array list. To calculate the size of an array list, we use the size method with parentheses after it. If elements are added or deleted during a traversal, objects may be outputted twice or missed entirely. Next, let's write some code to create an array list in memory. We start by declaring a variable of type list that will hold integer objects, and then initializing that with a new ArrayList object that will hold integer objects. Now we are going to add three numbers, 3, 1, and 8, to the array list on the heap. Now let's look at some code that will allow us to traverse the array list. We have a standard for loop. We start off by initializing I as 0, and we will continue as long as I is less than nums.size. .size is how we check the length of the array list. We remember that .length without parentheses is how we check the length of an array, and .length with parentheses is how we check the length of a string. The size is recalculated after each iteration of the for loop. So if we add or delete elements in the array list, the value that is returned here may change. We notice we are simply getting the values at each index and then outputting it to the console. However, we could do whatever we wanted with the data. Right now, the array list nums has a size of 3. However, like an array, array lists are 0 indexed. That means the first index is index 0, the next one is index 1, and in this case, the final index is index 2. This is why it's important to make sure I is less than the size of the array list, so we don't try to retrieve an index that isn't there. It's also important to understand that we must be cautious when adding or removing an index from an array list while we are traversing this. Because indexes will slide over when an item is either added or deleted, traversing an array list while we are adding or removing items may either cause an index to be returned twice or an index to be skipped. An important fact to know about ArrayLists is that we can't get or set to an index that doesn't exist. In this case, index 3, because there is no index 3. However, we can add using the two-parameter add method to one past the final index. In this case, we could add to index 3 because that is where a new element would be placed anyway. We would not be able to add to index 4 because there is no index 3. Now let's look at an example of using a for each loop to traverse an array. A for each loop will go through each index, pull it out into some sort of temporary variable. The type of temporary variable will depend on the data type that is stored in the array. We made temp value an int instead of an integer object, which is stored in the array list, because we are depending on autoboxing to unwrap the integer for us into an int. In this case, we are outputting the value of the variable temp value. Remember, changing the value of temp value will not change the value in the array list itself. Congratulations on completing the 3-hour Java tutorial. Please click subscribe to see videos on this channel. Also, there's a few more topics on the complete Java tutorial, so please click on that playlist to see if you might be interested in any of them.